Hello. Our next speaker is Free Ikanayaka. He is a member of the LXD at Canonical, and he will present dqlite, a distributed embeddable database. Please welcome.
Thank you very much. I guess you can hear me. So yeah, my name is Free. That's the real name, not a nick, as weird as it could sound. And as you mentioned, I'm a member of the LXD team at Canonical. LXD is a container management system for system containers. And as part of it, we started a sub-project called dqlite, when we had to implement clustering in LXD. So instead of having just one node running your containers, now you can have a cluster of them and it behaves coherently in a consistent way. We were using SQLite before, and so we thought it would be a good idea to keep using that model. Before I start, how many of you do not know about SQLite or SQLite? I don't see many hands raised, actually none, which is expected. Because yes, SQLite is one of probably the most widely used database in the world because of embedded systems, Android, and similar things. There are billions of deployments. And it's a very solid code base, very high quality, with a core team of maintainers that has been keeping up for more than 20 years now. There are many use cases for it. So the SQLite author advertises it as a replacement of FOPEN, in the sense that it's as easy to use as a system call to open a file, but in return you get a structured way to manage your data. So yeah, it's used in embedded devices, in agents such as LXD, or in desktop applications, for example, Firefox, Chrome, all use that to organize bookmarks and stuff like that, as you know. So what do you get with dqlite that you don't get with SQLite? So well, that's high availability. The main problem with SQLite is, of course, everything is local to your node, which is a good thing because it simplifies everything. Things are faster, etc. But it's also a single point of failure. For example, in LXD, if you put everything in one node, if you lose that single node, everything would be gone. Yeah, with dqlite, we distribute the data across all the nodes of the cluster. The data is replicated. So in case of failure of a node, there are automatic mechanisms for failover. And as long as your client can connect to another node in the cluster, you're good. So this is a very simple diagram of the classic way of using SQLite. So you have your application process. SQLite is a C library that you link. Depending on your application language, you will use bindings. So the original bindings are in C. And if you have an external client, either by an API or even command line, you can drive your application through it. With dqlite, the model is similar, except that you have more than one node. So you have a cluster of processes. your application will run on different nodes. Each node typically run one instance of your application process. And instead of talking to the SQLite API, you would talk to the dqlite API. Still, it's embedded in the process. dqlite is as well a C library which gets linked to your process. Inside dqlite, there is an engine which uses Raft to replicate the data, and SQLite actually to process the data, to offer you the SQLite engine. There's an important difference in that with SQLite, with the C API, you talk locally to your node. With dqlite, since it's based on Raft, we can talk about this later. You will have to connect to the leader of the cluster. So, is there a pointer somewhere? I didn't ask. Okay. No. Anyway, you have to connect to the leader of the cluster, which can be any of those processes, and that leader will be the one actually serving your queries. So it retains, dqlite retains the embedded part of SQLite, but there's no way you can keep the 100% local part. You need to go through the network, and this is one important difference. Should any of your processes die, the data in your database is replicated, as I said, and your process or your client, depending where you put the logic, can connect to the new leader, can discover the new leader, and go on with the computation. Okay, talk is cheap, show me the code. This is a quote from Linus Torvalds. So I will try to show you a very simple application. The goal is to demonstrate that you can write a Go program with 132 lines of code and using exclusively the standard library and the Go bindings for dqlite. And with that program, you actually get a distributed application with a distributed database and full fault tolerance. So the case study is just to make things a bit more interesting. A medical device. So one of the use cases I think dqlite would have is with the devices, IoT. You might want to have redundancy in your devices. So in this case, I picked a pulse oximeter, which I didn't know about before. So for those of you that don't know as well, it's a device to measure the oxygen saturation in your blood. So how much oxygen there is in your blood. I don't know much about details, almost anything, but for the curious, it works with a LED. It emits light through your body at different wavelengths. And since the hemoglobin in your blood absorbs light differently depending on whether it's bound to oxygen or not, the light will be absorbed differently, and there is another component at the other end, a diode that essentially reads the amount of light that was that passed through. So you can deduce the amount of oxygen in the bound to hemoglobin. The algorithm will be very simple. So we want to measure to perform this measurement at regular intervals. So we keep a history of the percentage of oxygen in your blood across the time, and we want to expose an API so that we can inspect the average. I don't know, in the last 5 minutes or 1 hour or whatever. The function to measure oxygen saturation is just a mock-up thing. So we imagine we have this fancy hardware that does what I described. And so it just returns a random value between 95 and 100, which is more or less the usual value that you find in your body. This is the function that we will use in the program. We initialize the database. This, for those of you familiar with Go, but it's the same with the other bindings. It just creates a table where we will store the measurement along with the timestamp when the measurement was made. And that's it. And we as I said, SQLite is very simple. You just have to open the database as you would open a file, and that's it. So this part is probably very familiar to the SQLite users among you. Then we have, of course, to save our measurements. So we have this persist saturation function. And we just perform an insert, simple insert of the value that we read. And since the schema has a default current timestamp, the timestamp will be saved automatically. And finally, the last piece, essentially, of the model of this little toy application is to retrieve the average saturation, and we just make a select query, taking the average over the last number of minutes or seconds or hours. That will be part of the query of the user. And that's basically it. You can put it all together. Your main function will initialize the database. It starts a Go routine. For those of you that are not familiar with Go, Go routines are, you can think about that as a thread of computations that go on in parallel with the rest of the program. So this is an infinite for loop that sleeps for some seconds and then makes a new measurement and saves it to the database, to the local database. And then we expose the service through the web with an HTTP handler, which just takes the tail parameter, which is how many minutes or seconds you want to average against, and then it returns the average in that window of time. So that's everything you need to do for this toy implementation. We can see it in action. I can build the program. Wait. So this is the tags libsqlite parameter. For those of you who know about Go, is needed because the bindings, it's a way to tell the bindings, please use the system shared library object instead of compiling the whole thing into your executable. So it's a bit faster. And I can then start the program. And if I perform a query, asking for example, the last 5 minutes of value, I get the average back. This will be refreshed every 30 seconds or whatever, and all the data is saved locally, as you might expect. So we have the history of measurements locally in your node. So as I mentioned before, this is simple and nice, but in a real world, the imaginary real world situation, what happens if the underlying storage media fails, and so you don't have access anymore to your data, and maybe they are critical for assessing the health of the patient or whatever, or if you need to do some maintenance over your devices and you need to replace it, but you don't want to interrupt the monitoring or stuff like that. Or another thing could be that the hardware that performs the measurement has some issues. Perhaps it's inaccurate, maybe even in small ways. So you might want to perform the measurements several times using several instances of the hardware and average the results to reduce the error in case one of them is not accurate. So in these cases, you want, of course, a cluster of devices, and that's a good use case for dqlite. So you would run the dqlite application in, for example, 3 instances of your devices, 3 pulse oximeters. Each oximeter would independently make the measurement. It would save the measurement in the distributed database. And yeah, even if one of them dies, it's still all good because the other have replicated data and can still serve your query. So the changes to the code that I just showed to you are minimal. One thing you need to do in your main function is to assign an identity to each of the instances of your application running in the cluster. An ID, a numerical ID, which needs to be unique for each node. This is basically used by the underlying Raft engine. Very simply put, to see which nodes have replicated which data. So just pass an ID to your main function, and we will pass it to the function that initializes the database. In turn, the function that initializes the database will need not just to connect to your local SQLite. Instead, it needs to start the dqlite engine. As I mentioned before, there is some networking going on, and the dqlite engine running in your process, in your application process, is the one which will be in charge of this network, and which is completely transparent to your application. So the start engine function, which I will show you in the next slide, will do that. There is another function called join cluster. You need to tell dqlite essentially which nodes are part of your cluster. So this will just be essentially the easiest way to do it. We could talk about membership management later on, but in this case, each node essentially tries to join the node. If it has already joined in the past, it's just a no-op. And the last thing, the third one, is to register the driver. This is also a Golang specific thing. So for those of you familiar, Go has a standard library package called SQL, and you can register different drivers for different database backends. So in this case, we want to register the dqlite driver, and we need to do it explicitly because some other libraries, they just register their driver transparently. For example, SQLite, there is a single instance of the driver object which can be shared, but in our case, you need to instantiate the dqlite instance, so you need to register the driver. Okay, this is mostly an implementation detail of Golang. Yeah, okay, you start the engine. So to start the dqlite engine, you need a couple of things. As I mentioned, you need the ID that you will use for the node. You need a network address. In this case, we just use a network address which is derived from the ID. We just append a number to the port. And you need a directory where you will save the data. So the data will not be saved in a regular SQLite database file. It will be saved in the Raft log. More about this later. Then there are a couple of options that you probably want to set. One is a bind address, which is what I said. This will tell the dqlite engine, please start listening to this network address, and all the traffic between nodes will go through that socket. And you might also want to specify the network latency. We can delve into this later as well. Essentially, this should be the latency, the one-way latency between your nodes. For example, if you know, I specify 10 milliseconds here because I will be running on localhost, which is fast. Anyway, depending on your network, you should specify more or less how much it takes to send one packet from one node to another. This is used internally by Raft to decide when it should consider the current leader dead, so another leader will step in. And that's it. That's it. As I mentioned, you have to join the cluster. You can use the dqlite Go client to tell the engine, please join the node. We don't join the node if the ID is 1, because node 1 will be the first node of the cluster. The cluster will have just one node at the beginning, so you don't need to join it. And the other nodes will just try to join, and if they fail, they just move on, assuming that they joined before. We leave out error handling and stuff like that for this demo. We register the driver. Okay, this is an important part. The Golang dqlite client will have to know the addresses of the nodes in your cluster. So in case one node dies, the current leader dies, it will connect to another node. In this case, we just hard code the list, but of course, you can organize your code as you want to know the current list of nodes, and you can wire it when you build the client. Okay, the total program, as I mentioned, is 132 lines of Go code, and it has everything. So I will show how it works. So instead of compiling this program, I will compile the other one. And as you see, the final binary is less than 10 megabytes. Okay. Anyway, these are the shared libraries it's linked to. You can notice SQLite, of course, and dqlite. And there are another few libraries which are the dependencies of dqlite, which are libuv, which is an event loop, the same event loop used by Node.js. So internally, dqlite is a single thread, asynchronous loop, event loop, and it uses libuv just for future-proof portability, and it's also a very good library. But it's a very, libuv, it's a very thin wrapper around EPOL on Linux. Then there is libco, which is a coroutine library. If you're curious why we use this, it's a one file long library adding support for coroutines in C. If you're curious, I can explain why, but it's not particularly important for now. And libraft, which is the Raft library that we wrote as part of dqlite for implementing Raft. Okay, we can start the first node, okay? And we can query it like we did with the other one, and it will return you the current average of the oxygen saturation. Then we can start another node, which, as I showed you before, will automatically join that cluster that was created by the first node, and a third node as well. So now all the nodes are online. And I can query them. So all of them will return the same value because the database is shared. So all the nodes see the exact same view of the database. From their point of view, it's as if they were talking to a local database. All the consistency properties that you have with a local database are maintained. Now, if I kill, so in this case, the leader of the cluster will be the first node because nothing disruptive has happened so far. So the first node, notice that it was the only one, so it became the leader since it was the only one. The other two nodes, when they joined, there was already a stable leader. They didn't need to do anything. So if I kill the current leader, sorry. Okay, anyway, it terminated. So what did I do? No sub-job. Say it again? So it was 2 because I didn't kill the first one. Okay, thank you. You can see that the first node doesn't reply anymore, but the other two do. Since they elected a new leader, they already had a copy of the whole thing, so it's fine. If the leader actually, the old node actually comes back, it will immediately join the cluster. The data, it will connect to the current leader, whatever was elected, and it will have immediate access to the current state of the database. And in the background, it will start to replicate what was missing. We can do the same exercise with with another node, and of course it will fail, but if we restart it, it will be good. Yeah, that's it for the demo. So we'll just pause for some time before I delve into more details. If you have questions already, we can decide in which directions to go.
So reads don't go through consistency.
Say it again?
Reads don't go through consistency.
Reads don't go through consistency. So you're asking what is the consistency model, essentially. Okay. So CAP theorem, not sure how many of you are familiar with it, but put it simply, in any distributed system, you have to make some choices around consistency. Since dqlite is based on Raft, the choices that are made are essentially consistency and tolerance to partition failures. But consistency is there. That means in Raft, reads are consistent. If you make a read, it will read the value of the last write. That means, in terms of SQL, if you have a transaction, if you use SQL transactions like we all know, things will work as you expect. So there's acid semantics, if you will, because the reads are served by the leader. This is probably the point that should make you understand why. The reads are served by the leader, so they always have the most recent value. It's possible to have reads served by non-leader nodes, so-called follower nodes, for scaling. There is a way to do it without sacrificing consistency, so retaining exactly the same consistency property as ACID, if you will. But it's not implemented yet in dqlite. So for now, all reads are served by the leader. Does it answer the question? Yeah. Go ahead. I don't have the microphones.
Can you dynamically change the number of nodes in the cluster as well with
Yes,
dqlite?
so let's see if we have something. No, I don't have probably a slide for this, but yes, it's the membership management lately got quite sophisticated. So as you saw, the membership management in the demo was absolutely a toy, but you can change membership dynamically. You can say, for example, one example that we use in LXD. I have 20 nodes in my cluster. I want 3 of them to be voting nodes. Those are the ones that are critical for your data. You will survive to the loss of one of those nodes. Or you can have 5 voting nodes if you want to survive the loss of 2. Then you can specify standby nodes, which are nodes that do replicate data, do write data on disk, but they don't participate in voting. So they won't be bottlenecks as far as latency is concerned. So you don't have to wait for them to complete their writes to reach the quorum that you need before you say, okay, this transaction is committed. And then you can also have spare nodes, which are just part of the cluster. They just sit there doing nothing. They don't replicate data. They don't participate in voting. And there is an API to assign roles dynamically to all these nodes. For example, in LXD, we have that code. So for example, when you shut down a node gracefully, at least we transfer leadership to another node if the node was the leader. We elect a standby node, which is a fast follower, to be voting, for example, to replace the voters, stuff like that. So there are advanced membership management options that you can use.
Okay. I'm curious, the Raft logs themselves need to be transactional, and I'm curious why you didn't use SQLite itself to process.
Sorry, I can't hear you.
The Raft logs themselves need to be transactional, and I'm curious why you didn't use SQLite itself to persist the Raft logs.
Okay, so the question is, since the Raft logs are transactional by themselves, why didn't you use SQLite itself to store them? So one answer is like the logs in Raft are a bit simpler, data model than SQL first, and also a bit different. The second reason is also performance. So you want the two bottlenecks of Raft are the network and the disk, of course. So everything you can do to minimize those paths, those hot paths, is good. In dqlite, I probably have a slide for this. Yes. Yeah. In dqlite, as I mentioned, it's a single thread engine. So it doesn't ever block. To do disk I/O, it uses a not very well-known kernel interface, which is the asynchronous I/O interface. The main system call involved here is IO_submit for those who knows, and it doesn't block. SQLite, by default, it blocks. So for example, if I have to write the commit to disk, I have to block, do nothing else. In the meantime, there's network going on, etc., etc. The choice of going single thread, there are many reasons. We can go through them separately, but I think this at least answers your question. Any other question? Okay. So I have a few more details. One important thing is
Excuse me? I have a question.
Okay.
I'm a bit curious about the need to use some external library like libcoro. Could you elaborate a bit about it?
Sorry, can you keep the microphone closer?
Yeah. Could you elaborate a bit about the need for the use of libcoro?
No, the lib is not libcurl. Is libuv. I think you mean this one. Libco. No, sorry, libco. Okay. So libco. How many of you are familiar with coroutines? Okay. For those of you that are not familiar with it, in C, there is no. So a coroutine is essentially a way to do concurrent computing in a single thread. Let's keep it simple. So you have some non-blocking part of code. It does its job until it can, because at some point it hits some blocking job to do, network I/O or disk I/O. Then that function or that coroutine pauses, is still executing in the same CPU, same thread, and it passes control to another coroutine, same thread, same CPU, and the computation goes on. So it's a way to, coroutines are lightweight threads. You don't have to context switch, you don't have to pay that overhead. They're really good for networking. Like famous web engines are based on this model, like Nginx, HAProxy, and stuff like that. So in C, there is no model for coroutines. You can't just stop in the middle of the function and start another function on another stack, like out of the blue. So libco is a way to, it has some black magic depending on the architecture. It will save the current state of all registers and stuff like that, all that kind of black magic, and it will transfer the program flow to another to an entry point in another function. Why I need this? This is related to the other question actually, because SQLite is blocking. So when I reach the point inside the SQLite code where I need to commit the transaction, instead of writing to disk, I have to ask Raft to do a commit, essentially. And that part is asynchronous in dqlite. dqlite is callback-based asynchronous. So there wasn't a way to stop SQLite there, just hanging for this without using threads. So I had to use the coroutine trick to do that. I hope that answers the question. Okay. Speaking of which, the SQLite version that dqlite needs is not the upstream one. It's a patched version for the reason I just mentioned. Not sure how many of you are familiar with the internal of SQLite, but when it comes to commit the transaction to disk, of course, it has an API for writing to the write-ahead log. I put some hooks in there, essentially, to call some custom interface that you can specify. In my case, it's the dqlite interface, so I can do all the magic. So the patch is very small. It's not a big one for now. And I've been maintaining it for a couple of years now, updating it at every release. And so far, I just rebase the code. And I occasionally get trivial conflicts, but that's it. That's a very stable part of the SQLite code base. And the patch is minimal for now. I would like to grow the patch a bit. We can talk about it, if you will, to add new ways of supporting replication, but that's it. Probably you might want to know whether this is going to be upstreamed. The answer is yes, eventually, hopefully. SQLite, it's a particular project. Quoting from them, it's not open contribution. The project does not accept patches. This is funny. Only 27 individuals have ever contributed to any code in SQLite. And of those, only 16 have traces in the latest release. Only 3 developers have contributed to non-comment changes in the last 5 years. So it's not something like you push a pull request on GitHub and it gets merged. It will be very difficult to get any changes in. So I will wait first when I'm absolutely certain that the patch will not change for some time in the future, and perhaps wait for dqlite adoption to hopefully raise and have some more arguments. Okay, we have a few minutes left. If there are questions or I think we're done. We can 5 minutes more. So okay, so for now the only language which is really supported by dqlite is Go, because LXD is written in Go. As I mentioned, when your application talks to the database, it doesn't talk to anything local. It needs to connect to the leader, and when they speak a wire protocol similar to Postgres or MySQL. I didn't pick MySQL or Postgres protocol for reasons. This is another topic. But there is a wire protocol that your client needs to speak. There is a Go client that speaks this protocol, but that's the only supported language. If you want to support your own language, you will have to write the client as for today, but the wire protocol is documented, and you can take a look at the Go one, for example, to have an idea how it works. It should be doable, but we would love to implement more clients in other languages, but for now we didn't have time. Yeah, one last thing is, as I mentioned, for now, the way data is replicated is by transferring pages of the write-ahead log of SQLite. That's good and robust, but it might be too much. For example, if your insert query just changes a few cells in the B tree, so you change just a few records, that might be overkill. So I would like to implement B-tree based replication. So in the transaction, I just look at which cells were modified, and I just replicate a logical representation of the change, pretty much like Postgres does, I think, more or less, or even statement-based replication. Those are way smaller payloads to transfer over the wire and to write on disk. It depends. This needs to be benchmarked, because often it doesn't matter much if you transfer just a few bytes or a full page, because network and disk, but that's it.
So,
yeah.
Okay. Thank you. Thank you, Free. And time for more questions. Oh.
Are there constraints in terms of hardware or architecture to run?
Are there constraints in terms of hardware or
architecture?
Architecture, no. The only constraint is for now is the operating system. We are targeting Linux because of that asynchronous disk I/O, but that could be ported to other operating systems as well. But no, architectures, whatever you want. We run it on ARM, we run it on S390, whatever. Yeah, whatever Linux supports.
Have you benchmarked the performance hit for the Raft protocol? And what kind of extra latency does that add to queries?
So yeah, as I mentioned, your bottleneck will be the disk and the network. So compared to SQLite needs to do a disk write. More or less that's the same. dqlite needs to do a disk write on any node. That happens in parallel. So that part, you can expect more or less the same performance as SQLite. The overhead will be one network round trip, because you need to propagate the change and get an answer to decide that there's a quorum. So it's SQLite plus one network round trip. That's more or less what we observed.
So first, thank you for the talk. I want to do a question about asynchronous I/O. I'm not used to asynchronous I/O in C, but in other platforms. How do you manage to, can you hear me? you hear me?
Barely.
Can you hear me?
Yeah, now yes,
Okay.
better.
How do you manage to perform blocking and unblocking operations using libco? Do you have like worker threads when you perform only the synchronous blocking operations, or?
So the question is, how do you perform blocking calls using libco? The thing is, you don't. dqlite does not use any blocking system call. Say it again? Yeah, that's the reason why we use libco in the first place. When you enter the commit path of the SQLite transaction, the SQLite logic code will pause there, the registers will be swapped, and the Raft engine will run, so to speak. That code will sleep there. Nothing else will happen. Also the readers, well, the readers actually go on in parallel, but other writers will be blocked like SQL. So SQLite will be frozen in that particular spot in the SQLite code. So that's, from the point of view of SQLite, that's blocking. But from the point of view of the CPU, I'm just swapping the registers and going on with something else, okay?
Okay, time is up. Thank you again.
Okay. Thank you.